Hello everyone, I'm Dr. Mohit Kapoor. I'm a junior resident at Department of Radiodiagnosis, AIMS Bibinagar, Hyderabad, and today I will present my series of seminars on the topic X-ray physics. So first starting with the basics. What are X-rays? So X-rays are EM radiations that are set up in space by oscillating electrons, and a single unit of this radiation is called as a photon. So here we have the EM spectrum, and we can see above the visible spectrum we can see UV, X-rays and gamma rays, and we can see X-rays they all have very high frequencies. So we can see X-rays having very high frequency, and so these are EM radiation, so these have properties similar to EM radiation. So the only point which I want to cover here is that X-ray will cause blackening of the film. So it should be kept in mind, whenever X-rays are interactive with the film, they will cause blackening of the film, and wherever X-rays cannot reach, that part of film will remain white. Next, the component of the X-ray machine. So this is the X-ray system which is at our institute, and we can see we have an X-ray tube over here. We can see screen in the front. We can see the X-ray tube over here. Inside this X-ray tube, we will have main cathode and anode, and which will cause production of the X-rays. And when X-rays will come out infraredly through a window here, and X-rays will come out from here, and while they are coming out, we will have filter over here. And the importance of this filter is that it will filter out all the lower energy X-ray radiations. And then we'll also have a collimator over here. The importance of this collimator is that we will know where our X-ray beams will hit. Then X-ray beams will come, interact with the patient, they will get attenuated or reduced in intensity, and this ultimate signal will reach our detector system over here. And this detector system will process the signal and show it on our screen over here. And so ultimately we will see it on our screen. Before starting the X-ray projection, we can also change the KVP and MA at this level. And we also have a transformer rectifier combination, X-ray generator over here. The importance of that is that it will provide a constant uniform supply to the system. So ultimately my talks will also be in following parts. I will first talk about the X-ray tube. What is an X-ray tube? What are the components of X-ray tube? Then I will talk about how X-rays are produced in the X-ray tubes. And then I will talk about what is a filter and what's the importance of the filter. And I will also talk about the collimination. What is a collimination? And then when X-rays are coming out, they will interact with the matter. And so my next talk will be on interaction with the matter. And then they will be getting the signal will reach our detector system, and so ultimately my next talk will be on the detector system, and ultimately the image will reach our system over here, our control panel over here. And so my next talk will be on the control panel, transformers and rectifier. So I will cover X-ray tubes, production of X-rays, filter and collimination, X-ray interaction with matter, X-ray detector system, control panel, transformers and rectifier. So the first seminar which I will cover here today is X-ray tube. So this is the X-ray tube which is our at institute, and this is basically a just protective covering outside, or a protective housing outside. And this protective housing will contain a glass enclosure or glass tube like this, and inside this glass tube we will have a cathode and an anode. So ultimately our X-ray tube basically will have four components. We will have a protective house or protective shell like this. We will have a glass tube. We have a protective outer shell. We will have a glass tube, and this glass tube will contain a cathode and an anode. So first is a protective housing. This protective housing is lead line. The importance of that is when X-rays are produced, they are transmitted in all direction, but we don't want that. So this all is covered by lead, which will prevent the transmission of this X-ray beam. But we will have inferiorly we will have a window through which X-ray beams can pass. So ultimately protective housing will protect, it will prevent the X-ray leakage. Second is the glass enclosure here. So this importance of this glass enclosure is that we will have vacuum inside this glass enclosure. So if we talk about how X-rays are produced, so electrons will be formed at the cathode level, and they go and accelerate towards the anode level, and they will go and hit the anode, and that will cause production of X-rays. So if we don't have vacuum inside this tube, if we have some air or air inside, then atoms of this air or electrons of this air will interact with the electrons which are crossing the tube are going to hit the anode. So ultimately the X-ray beam which we will get finally will not be uniform. It may be high, may be low, but it will not be uniform. And so to prevent that, we want vacuum inside the tube. So third part is the cathode part. The cathode will have a filament and a focusing cup. The importance of this filament is that this filament is made up of tungsten, and whenever we give filament current, this is 10 ampere current to the filament, then this filament will start heating up. And when we heat it to 2200 Celsius, then we'll start releasing the electron around. And then this process is called as thermionic emission, that we will have emission of the electrons when we heat the filament to a certain temperature. Then second component is the focusing cup. This focusing cup is also having negative potential like the filament and the electrons. So this will repels the electron towards the anode. So ultimately this will repel the electron towards the anode. But you should know that this is not the main focusing point, not main point which will accelerate the electrons toward the anode. The main energy which will focus the electron or accelerate the electron from cathode to anode is the potential difference which we will create. So we will also create potential difference between this cathode and anode component, and that is the main accelerating factor which will accelerate the electron towards the anode, and it will cause it will go and hit the anode. Anode will have a main molybdenum stem and a small target disc. This target disc is made of tungsten and rhenium combination, and when electrons strike on this target disc, it will cause production of the X-ray. We also, when electrons are accelerated towards the anode, then they are accelerated, so they will have some velocity, and they will have energy, and this energy will be in the form of kinetic energy. So ultimately, when electrons are traveling toward the anode, they have some kinetic energy, and when they hit the anode, they lose all its kinetic energy. The 99% of the kinetic energy is converted into heat, and just 1% of this kinetic energy is converted into X-ray beam. So ultimately we will have a lot of heat producing, and so ultimately this anode stem is so that it can remove the heat. So that's the importance of the anode stem. So these are the four components of the X-ray tube. So how X-rays are produced? We will provide a filament current which will heat the filament to 2200 Celsius. This filament will heat, it will start releasing electrons, and we will by process of thermionic emission, and this electron cloud which will appear surrounding this filament is called as space charge or Edison effect. Then we will apply a tube current which will accelerate the electrons from the cathode towards the anode, and will cause a bombardment of the electrons to the anode. This electron will have a velocity of approx half of the speed of light. They will go and bombard with the anode, and when they interact with the anode, all of the kinetic energy, 99% of the kinetic energy is lost in the form of heat, and this 1% of this kinetic energy is converted into the X-rays. And this X-ray will be transmitted in all direction, but it will just actually go out from the system only through the window. Rest everywhere it will stop by the protective housing. So ultimately X-rays are produced and they come out from the window. So that's how X-rays are produced. But you can see, as this was the normal system, as we are hitting the electron, the anode will start getting heating, and it will start to get heated up. And that was a problem which we face in the conventional X-ray tube. The anode used to get heated up very easily. But now we have a modern X-ray tube, and we can see here the anode is rotating, and the anode started rotating so that we can have better heat transmission. And so that's the benefit of a modern X-ray tube, that there is better heat transmission. The filament is made up of copper or tungsten. We prefer a tungsten filament because the tungsten filament will have a very high tensile strength. This is the most important point for tungsten filaments, that they will have a very high tensile strength. And this is important because then the tungsten filament can be coiled very easily, and they can be coiled to multiple loops, and this multiple loops will greatly increase the surface area, and so more and more electrons will be available for thermionic emission. So ultimately we prefer tungsten filament because mainly it has a very high tensile strength. But second point is it also has a very high melting point. So whenever we are giving it a filament current, so it will start to get heated up, but it will not melt, and that's the because it has a very high melting point. And third point is also that it has also high atomic number, so there are also a lot of valence electron in its outer shell, but that is not important. The main point why we use tungsten filament is because it has a very high tensile strength. We use a nickel or molybdenum focusing cup because they also have a very high melting point, so they will also heat but they will not melt. But when they when they heat, they will develop negative charge, but they will not release electron, so ultimately they will get negative charge which will repel the electron towards the anode. So that's the reason why we prefer molybdenum focusing cup. Anode, basically rotatory anode. We can have a stationary or rotatory anode. We prefer rotatory anode. So rotatory anode will have a target disc and a molybdenum stem, but it will also have a copper rotator, and this rotator will move because of the lubricant bearings, because of the bearings, and these all bearings are lubricated by liquid silver. So ultimately we have a target disc, which target disc is made up of tungsten and rhenium, and this is in 90 into 10% ratio. Then we also have a copper rotator, and this copper rotator is blackened so that we can have more and more heat loss. And this we have bearings also which help in movement, and this all is lubricated with the help of silver. So that's how anode system is made up of. But one thing we should also keep in mind is we also this target disc is not straight. It has a beveled edge of approximately 6 to 20 degrees, like we can see here. The anode is not straight, it will have a beveled edge like this. And this beveled edge is because we want to make use of a line focus principle. But due to beveled edge, it also causes anode Hill effect. So we will talk about the line focus principle and anode Hill effect. But first, we should know how anode cools. So anode can cool by conduction, convection, or radiation. But the main mechanism by which the anode cools is the radiation. So main mechanism by which the anode will cool is the radiation, but can also cool by conduction and convection. Starting with the line focus principle. So this was actually a dilemma because we wanted a larger focal spot. A larger focal spot is a point where the electron beams will go and hit the anode. So we want this area to be more, because if this area is more, there will be more and more heat dissipation. So we wanted a larger focal spot. But if we have a very large focal spot, the quality of the radiograph will not be very good. So for a good radiograph, we want a focal spot to be very small. So this was a problem which we had, and this was solved by making the edge of the anode beveled. And so ultimately we had a larger actual focal spot where the electrons were hitting, but effective focal spot which was going to be used in making the image was very small. So ultimately we had a larger actual focal spot, this one, and a very small effective focal spot, this one. And line focus principle says that this effective focal spot is equals to sine theta into actual focal spot. So ultimately line focus principle says that this effective focal spot equals to sine theta into actual focal spot. So ultimately, if we want effective focal spot to be small, we can either decrease this actual focal spot, but if we decrease this actual focal spot, the heat dissipation will also decrease. And we can also decrease this angle, that is the sine theta. But if we decrease this angle too much, we will have decrease in the field size also. Like we can see here, this is the normal field size, but if we decrease the angle to too much, then effective field size also will decrease. So if we want to cover larger area, we will not be able to cover large area also. So this is something we should keep in mind. We cannot decrease the angle also too much, and we cannot also decrease the actual focal spot too much also. The angle which we normally keep is approximately 6 to 20 degrees. And now coming to the anode Hill effect. Now whenever electrons will go and bombard with the anode, so it will cause X-rays, and when X-rays are coming out, so the anode Hill effect states that the intensity of these X-rays will be significantly less at the anode edge as compared to the cathode edge, and this is because the X-ray traveling towards the anode edge will have to will have more target material to cross, and therefore it will attenuate, matlab reduce in intensity more than those which are traveling to the cathode, which have very less area to cross. So ultimately when x-rays are going to cross, because here we have less area to cross, so this part of x-ray will have more radiation, more intensity, whereas as this part is getting more and more attenuated, so this area will have lesser intensity. So ultimately our x-ray beam will not be uniform. It will have more intensity x-rays towards the cathode and lesser intensity x-rays towards the anode. And this was the anode Hill effect, and this can be varied also. Like if we increase, like this was a normal angle, and if we increase our angle, so ultimately lesser our x-rays have to go through the anode part. So ultimately if we increase the angle, this anode Hill effect will also decrease. Or we can increase the SID distance also, and if we increase the SID also, then ultimately our anode Hill effect will decrease. Or we can cause collimation also. Collimation will also cause decrease in this anode Hill effect, because we can see, like suppose if it's 1 and it's 10, so this will be approximately 3 and this will be approximately 8, so there will be very high difference here. But if we go more, if we increase the distance, suppose this is 1 and this is 10, so this will be around somewhere around 4 and this is somewhere around 6, so difference between them both will be very less. And same is the principle of collimation also. Difference between them both is high, but between these both will be very less, and that's how also we can decrease the anode Hill effect. Or we can also clinically use this in our advantage also. Like if we know that we will have more intensity of x-rays towards the cathode end and lesser intensity of x-rays towards the anode end, so we can project our patient also in this way, that more denser tissue or more denser structures will be towards the cathode end and lesser denser tissues will be near the anode end. So like if we are doing pelvis radiograph or we are doing spine radiograph, so we will put more denser pelvis bones towards the cathode end and lesser denser anode component, lesser denser spine component towards the anode part. Or we can use in ankle x-rays also. We know near the ankle we have many bones, so that ankle we can keep in the cathode part, and the finger parts we can keep near the anode. And same we can use in mammography also. The thicker chest wall is kept near the cathode and breast tissue is kept near the anode. So this is how also we can clinically use the anode Hill effect. Now I've covered the first topic, that is the X-ray tube. Now I will put some points here, true and false, and you have to read this point with me, and then just like pause and see if it's true or false, and then I will tell how is this true or false. So cathode contains filament and focusing cup. Filament has a negative potential. Focusing cup has a negative potential. A minimal filament temperature must be exceeded before the tube current flows. Tungsten is used as a filament because it has higher atomic number. Electron is formed by a process of thermionic transmission from the cathode. Filament current and tube current are not same. Filament current is applied across the tungsten filament and affects both the energy and number of electrons. Tungsten tube current is applied across the X-ray tube from cathode to anodes and affects both energy and number of electrons. So I will show the answers now. So first point, cathode contains filament and focusing cup. That is true. It has both filament and focusing cup, and both filament and focusing cup will have negative potential. Focusing cup, as it has negative potential, it will also repel the electrons, so that's the benefit of focusing cup also. A minimum filament temperature must be exceeded, that is true, and this temperature is 2200 Celsius for tungsten. Tungsten is used as filament because it has higher atomic number? No, it is used as filament because it has higher tensile strength. So it can be coiled easily. It has higher atomic number also. But the main reason why we use tungsten as filament is because it has a higher tensile strength. So we can coil it into multiple loops and we can effectively increase the effective surface area. Electron is formed by process of thermionic emission, not transmission. Filament current and tube current are different, that is true. Filament current is applied across the filament, this is approximately 10 mA, and affects the energy and number of electrons, that is false. Filament current will cause heating of the filament and will cause emission of the electron. But electrons will, there will be more number of electrons released, but it will not affect the energy. Energy depend on how fast the electrons will go from cathode to anode, and it does not affect the filament. It is not affected by the filament. So filament current will increase the number of electrons, but it will not increase the energy. Whereas if we increase the tube current is the current which is applied between the cathode and anode. So if we increase the tube current, then more and more number of electrons will be released from the cathode, and they will go and hit the anode faster also. So it will increase the number of electrons also and energy also. Next set, our target disk of anode is made up of tungsten and rhenium in 17 to 30% combination. A rotating anode results in larger focal spot. A rotating anode results in higher heat dissipation. Heat is removed from anode mainly by convection. Rotor motor has blackened surface to increase radiant heat loss. The rotor bearings are lubricated by oil. The effective focal size is regulated by target angle, target size, filament size, and applied kVp. So coming to the answers, the target disk of anode is made up of tungsten and rhenium. That is true, but the combination is 90 and 10% combination, not 70 and 30%. A rotating anode result in larger focal spot. That is false, because if we are rotating the anode, the effective focal spot is still remaining the same, but we are just having more and more heat dissipation. So this is false. It will not affect the focal spot. The focal spot will remain the same, but we'll have more and more heat dissipation. Heat is removed from the anode mainly by convection. No, it is removed mainly by the process of radiation. Rotor motor is blackened. That is 2 point, to increase the radiant heat loss. That is true. The rotor bearings are lubricated by liquid silver and not oil. The effective focal size, we know line focus principle states that the effective focal size depends on the angle, that is the target angle, and the actual focal spot, which will depend on how big the filament we have. Actually, in our system, we have two filaments. We have a larger filament and a smaller filament. So depending on how much focal spot we want, we can change it from larger filament to smaller filament also. So, and that will change our actual focal spot also. So effective focal spot depend on the target angle and the filament size. It does not depend on the target size. And actually, effective focal spot size should not be regulated by the applied kVp. But here the concept of blooming comes in. Blooming refers to the increase in the focal spot that occurs when tube is operated at high MA or low kVp. So this is also something we should keep in mind. So if we have a very low kVp or very high MA, then also our focal spot size will differ. And this is known as blooming. So this is what I want to discuss in my first seminar. So thank you very much.